way we make iron today is by melting it, with coal at 1600 degrees Celsius, as we were pointing out. And what we developed was a process in which instead of melting anything, we bring the feedstock, which is iron ore, and getting that into solution instead of melting it. And once you get into the solution, you then have an opportunity to seamlessly pair that with source of electricity that's intermittent, i.e. renewable, meaning now you can, just like an electrolyzer or a battery, you can load follow the availability of electrons, because now we no longer are operating at 1600 degrees Celsius. Now, when we bring this into solution, our solution that we're operating that part of the plant is at about 60 degrees Celsius, definitely less than boiling point of water.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm excited to be here with Sandeep Nijhawan, the CEO and co-founder of Electra, a company focused on decarbonizing steel production. Steel making is one of these hard-to-abate heavy industry sectors I keep hearing about needing more focus. It accounts for something like 8 to 10% of global emissions, and the majority of those emissions are from iron production, which is an input to steel making. Electra's process of electrowinning can be run on renewable electricity and produces 99% pure iron. One thing I'm particularly impressed by is the speed at which Sandeep and his team have made progress. They founded the company in 2020, if I have this right, Sandeep, in a garage. Today, you have over 130 employees, 2 pilot plants operating in Colorado, and you recently closed your Series B of $186 million in funding. Sandeep's background is also impressive. He has a Ph.D. in mechanical engineering and an MBA. Prior to Electra, he was the president of Aqua Hydrex, developing electrolyzers for green hydrogen production. He was also an operating partner at True North Ventures. Prior to that, he founded and ran a company in energy storage with the goal of supporting the growth of renewables. Sandeep, it's a pleasure to have you here today. Thanks for joining.
Well, thank you for inviting us here. I'm really excited to be here and part of this conversation, Dylan.
So you actually started your career in LEDs, I noticed.
Yeah.
When I was looking through your LinkedIn. So you founded a number of companies. The first company you founded was developing novel LEDs.
Yeah.
And then it's clear in your sort of recent career moves, you've been very climate focused. I'm curious, early on, was there a sustainability focus in the LED space, or is that something that kind of came into your career later?
No, I think my career actually goes prior to LEDs, and I started my career in semiconductor industry. So after graduating from my Ph.D., my first job was in semiconductor industries, and I was building devices that are today used in every cell phone and every computer you can think of. A lot of material innovation going in to make these devices faster, more memory that can be stored, and so on and so forth, every few years. Driving the Moore's law forward, where I started my career. Fairly early on in my career, I started to realize that I wanted to sort of transition into something that would have, in put it better ways, like more impactful climate impact. And back in early 2000s, clean tech was the word that we used to use. And LED being a semiconductor device and was also tied to energy efficiency of lighting, was a very nice foray into going from a silicon transistor to a compound transistor. And that was really my first transition into building startups. And during that period, I kept on getting pulled back into doing traditional semiconductor industry. After I started my LED career, I just started getting more opportunities, also still in the semiconductor space. But in 2014, I actually made a personal commitment and a professional decision that if I can, I will essentially focus my remainder of my professional career towards, what we call energy transition today. And it sort of starts off with a conversation I was having with my son, who was at 7 years old. And that sort of conversation just led me to like, all right, I just need to go all in on this. And since then, never looked back in terms of being in this space.
Yeah, I have kids, and it definitely kind of changes your perspective on this stuff.
It does. I mean, and, just to share that with you, that conversation was, my son in 2014 would be like 8 years old. Home dinner conversation. He wanted to understand what's bad about driving a car with, gas. And then he was trying to understand, the impacts of that vis-a-vis with respect to the climate change. And I started to explain to him, how that accumulation of, the CO2 emissions we have accumulated over hundreds of years of plus of industrial revolution has really now causing a greenhouse effect. And as a result, our planet is warming up and we are seeing drastic changes to the climate. And that conversation, he started crying. It's like, oh my God, the world is coming to an end kind of a thing. And like, okay, what can we do? Kind of a thing. And it was, in a way, at that moment, partly to help him stop crying, and to say that, look, I will do everything I can.
You're like, I got this. Don't worry.
Don't worry about it. It's going to be tough, but hey, let's do our part. And I'm doing my part, and I'm going to do more of my part to make sure that I leave the world in a better place than where it is today. And that was really the crux of like, all right, lots of opportunities come along your way, lots of ideas come along your way. As an entrepreneur, you have, lots of things you want to work on, but how can I focus myself towards, things that would have impact related to energy transition, related to climate change is really when I made a commitment, a pledge, and I haven't looked back since then. It has been pretty fruitful journey so far.
And so is that when you started the energy storage company?
Yeah, that's true. That's when I started the energy storage company, joined a venture capital fund that was focusing on energy, water as a big themes from investment perspective. And as an entrepreneur in residence in that venture fund, sort of work with a few of my colleagues to build the business plan for this energy storage company. And that was for grid scale application and then help with other energy investments there as well. And through that vehicle also looked into hydrogen and so on and so forth. And really in that period and since then, following a thesis around the climate transition and what is critical in terms of what's the critical constraint that one has to go address. And one way or another, including what we're working on Electra, is really tied to that thesis in some ways. And so these are all derivatives of the same thesis I've had in terms of what I can do and help with this transition and what the world needs as well.
And then I know you worked in kind of electrolyzers for hydrogen production and now steel. I'm curious, what was it about?
Yeah, so I think in 2020, a pandemic has just started. So this was peak of the pandemic, Q1 of 2020. A lot of time on hand. Most of us were home, starting to think about the next thing I was going to work on. And it quickly led me to looking at iron and steel, given its impact in terms of its emission. But even stepping back for a minute, the thesis around I've had for now almost 10 years is that as we think about climate change and this energy transition, a lot of the solutions that we're looking at, there's a common thread on them that they all pass through electrification as a route. So electric vehicles is a good example of that. Storing energy, renewable energy in a battery, another example of it. Taking that electricity, green electricity, and breaking water and making hydrogen as a fuel is another example of it. You can take electricity to carbon capture and on and on, So electrification is critical to energy transition, and renewable electricity as a result plays a huge role in it, but it has intermittency as a challenge. It is not a base load. It is not available 24/7. So as you think about pairing that renewable resource to the solution and the applications that the world is seeking, you look at batteries as a way to do that, for example. But when you look at industrial decarbonization, you realize that most of those processes, including steel, including cement, they operate at a very high temperature, which inherently becomes very difficult to pair with an energy resource that is not available 24/7. So how do you do that? So as I was thinking in 2020, that was sort of in front of me as well, is like, here is a industrial process which is one of the hardest to abate sectors. Steel making emits, as you said, 8 to 10% of emissions. And how do you electrify that? How do you decarbonize that and build a lower emission process from the ground up? And it was really continuation of the thesis that I've had is, how can we use renewable electricity in a way, meaningful way to help with this transition? So that was the genesis of Electra. The challenge with Electra, obviously, when we started was that I didn't know how to do it. It was like, we should do it, but not clear in a way how one can do it. So it started with a problem statement, more or less, a very bold, I would say, vision that perhaps we should go down this path and explore. Can this be done? And if it can be done, that would be very enabling. So that's really was the starting of Electra, starting in a garage, starting to think about how can this be done in a different way.
I mean, where do you even start? If you've got this big problem statement, it's sort of this massive challenge.
Yeah.
Many people would love to know the answer. What, you're in a garage. What do you do? What's day one look like?
Well, I mean, I think part of building a company, I would start even before you even think of a solution. As unfortunately, as an engineer, somebody gives you a nail and a hammer and you just want to go put that on the wall without asking the question, should you or do something else? My first 6 months was really trying to understand the problem statement quite deeply and understanding what are the adjacency and the constraints that the industry is also facing, and developing in a way a market hypothesis where the puck is going, not the where is puck today, where is the world today, but the where the world has to go. Because this transition is going to take another 20 years, 25 years, 30 years. So you can't just think about what are we doing today kind of a situation. So you have to start with that first as a market hypothesis. And then with that in mind, build the boundary condition around what attributes a good solution needs to have to help solve that problem on where the world is transitioning to. And with that boundary condition, then building a team to start thinking about, you have to find a solution within this boundary condition, and letting loose the team with that and the resources, but also being very practical about it. That, look, guys, if we can find an answer, that's okay. You shut it down. You fail fast. There are a lot of problems to solve for. You go tackle this problem and seeing what can you do. So having that courage to be able to say that, look, it's possible that we may come empty-handed. That's okay. That's okay. And then you go try something else is what I pitched to my first sets of investor, that this is very, very high risk. And the good thing was that I was able to put together, with help of my other co-founder, a small team, about 10, 15 people. First thing that proved to me was whatever I was thinking before starting the company will never work. So that was pivot number one. 3 months in.
Okay, moving on.
This is not going to work, Sandeep. There are the reasons why. And then understanding those reasons, I think the team was very innovative and creative to be able to break that problem down and come up with a different way to solve the same problem. And just to understand the contracts with what we developed versus what it is today. As you mentioned in your opening monologue, what we're trying to develop, what we're trying to seek is, how do you get to iron? And iron is really a key essential for steel. batteries, all the modern infrastructure we know. And the way we make iron today is by smelting it, with coal at 1600 degrees Celsius, as you were pointing out. And what we developed was a process in which instead of melting anything, we bring the feedstock, which is iron ore, which is what we dig out of the ground. So that's iron and oxygen that has been bonded together for millions of years on our crust, and getting that into solution instead of melting it. And once you get into the solution, you then have an opportunity to seamlessly pair that with source of electricity that's intermittent, i.e. renewable, meaning now you can, just like an electrolyzer or a battery, you can load follow the availability of electrons, because now we no longer are operating at 1600 degrees Celsius. Now, when we bring this into solution, our solution that we're operating that part of the plant is at about 60 degree Celsius, definitely less than boiling point of water. So there are a lot of things you can do in terms of pairing that seamlessly with renewables. That was one part of the equation we were looking for. The other part was that it dawned on me that we do that type of processing for every other metal other than iron. So this is how actually, by going into a solution form, electrowinning, hydrometallurgy as a science was developed to be able to process every other mineral that we use today. So you take zinc, you take copper, you take lead, you take nickel. That is how we process those minerals. And we're developed that methodology largely because, unlike iron ore, for which there are high grades of it available on the crust of the planet, meaning very high content iron in the iron ore, most other minerals are lower grades. So if you, for example, were to mine for copper, if you get 1% copper in that ore, that's great. That's a great feedstock. It means that the rest of all the stuff has to be removed and purified and to get to that 1% copper. Zinc is about 7%. Okay. Now in iron making, iron ore typically in Pilbara and Amazon river basins, you can actually dig out of the ground, which may be 60% iron content. So very high grades are actually naturally available. So the world for the 500 years figured out that if that's high iron content is available, best way is just melt it. Okay. And because coal was cheap, that's the easiest way to purify that and make it into iron. But an agency problem, this is what we discover in our market analysis, is that those grades of iron ore actually are also running out. And when we dig those types of ores today, we leave heaps and heaps and mountains of material that is not up to the grade that you would want to melt them. Okay, meaning that they have higher impurity content, so it's not economical and efficient to melt them. So we're reading stockpiles of, I would say, still relatively high iron content, in the mines that remains underutilized. Okay. So that was the other thing that we were able to connect, is that we are able to use, because we're doing a solution processing, which was invented for lower grades of ores, we actually brought that to iron making. And by doing that, we are able to use a resource that is heavily underutilized. I mean, we are talking about mountains of this material that are sitting in mine, billions of tons over the last.
It's like a waste product.
Well, the industry doesn't call it a waste. It just like it's an underutilized resource that doesn't feed into today commercial grades that are used for steel making.
Okay.
And we are able to take that. But that feedstock, we then, because it's an electrowinning, meaning we're passing electricity through the solution, we have a solution form. We pass electricity to the solution, we're able to extract the iron. The iron that comes out is pure metal. It has no impurity. It's like 99.9% pure metal, which is what you need to make high quality steel. So we then feed forward something that is quite impure as a feedstock, but we feed forward only pure metal, which is what you need for steel making. And in the process, what we are also finding is that these ores have lots of other things in it. So what else is in it as an impurity today? We think of them as waste, but we think of them as, can we further refine them and create value of it? So that's really the journey we have taken over the last 5 years of starting from a vision of how can you take something that is a 1600 degree C process, bringing down in an operating temperature so you can pair with renewable energy. But not only that, address the sustainability of mining and creating value and extending mine life of things that are already been dug out of the ground, and hence use that as a feedstock to make the critical constraint we need to get rid of those emissions or eliminate those emissions.
So just to play it back to make sure I understand, it sounds like you're taking kind of this underutilized ore, which is a lower grade than what it would typically go into a blast furnace. And you find it in mine tailings, or it's in kind of these big mountains of mine tailings. You put that in some kind of bath, dissolve it into water or some kind of solution.
Yeah.
And then the pure iron, collects on an electrode or something in that bath as you apply a current.
Yeah. So let's step back. I mean, you got that right. You take the ore, it's in solid form. And our first step is we pre-treat this ore through a step. And all it does, it allows us to improve the rate at which we can bring that ore into the solution form, because we're trying to go into solution form. And the way we dissolve the ore in the solution form is we're using an acid. Okay. And I'll come back to the acid in a second. So our acid gets consumed and you're dissolving the ore into solution. Now, what you get in the solution is, first of all, things that don't dissolve, so you can filter them out, but things that have already been dissolved, which is iron-containing solution, as well as other impurities that have now come into solution. So then we go through a purification step and we remove impurities that we don't want that can potentially hinder with extraction of iron step, which will be the next step. And that's a very standard process that we use. This is a very similar thing other mineral refinement industries use. And we are taking that approach into iron making, essentially. This next step we do is now we have a purified solution containing iron. So this is in dissolved state. We dip in that solution a plate of steel, essentially. Okay. And we pass current through it. And in that process, what happened is the iron from the solution then goes deposits on that metal electrode. So it's like an electrolyzer. You pass one-way current, and what is in the solution, i.e. your electrolyte, that's iron containing, iron then goes to the electrode. And then we remove this plate out. Okay, now so we harvested pure metallic iron onto this plate. And then we are able to then detach iron off of this plate and put that, electrode back in to continue to harvest more iron out of the solution. And what we do is in this process, we then also regenerate the acid. So in any electrochemical system, there are usually two electrodes. One is a negative side and one is a positive side, just like a battery. So on one of the electrodes, we're extracting iron, but the other electrode has a counter reaction, which then helps regenerate eventually the acid. And then that acid is then sent back to the front of the plant to redissolve more ore. So we actually don't bring any acid into the plant. The only thing we bring into the plant is the ore and electricity. And then what we take out is the byproduct of one of the reactions is oxygen, pure oxygen. So just like a hydrogen electrolyzer, you have oxygen evolving. So pure oxygen and pure iron comes out as a byproduct. Once we have this pure metallic iron, we feed that forward into electric arc furnace, not blast furnace. It's an electrically powered smelting process where that iron is mixed with recycled steel, like scrap that we collect. So it helps with the overall recyclability and circularity of steel. And then that is recasted into new steel.
Do you do that process? Does Electra do that process? Or you provide the iron to steel makers?
We provide the iron to the steel maker. So one of our, for example, publicly disclosed investor is Nucor. And Nucor is the largest EAF steel maker in North America. And we feed that iron into their process. And then they convert that into steel. So where Electra fits into the value chain is we are between the miner, folks that are digging the ore out of the ground, and an EAF steel maker. And that's the second way to make steel. Blast furnace is one of them that we are trying to displace. But the other way is to recycle the scrap and the steel, which is the electric arc furnace. And we are compatible with the second approach that is electricity powered, helps with circularity and reuse of steel making eventually as well.
So your innovation was really applying this kind of electrowinning process that had been developed for lower grade mineral extraction, applying that to iron ore.
We do that in the world today for many of the metals, but not for iron. And so we had to go solve specific issues related to iron making.
Okay, yeah, I was going to ask, did that present a whole new batch of technical challenges to apply it in this way? Or?
To say the least, yes.
Okay.
Yeah, there are a number of challenges. One was that, the iron ore doesn't like to dissolve that rapidly in acid. So it's a very slow process. So we had to figure out a step to get it into solution in an economical way in a small amount of time. So that was one. The second innovation was around that while iron is difficult to get into the solution, converse is also true. It wants to come out of the solution very quickly. So you have to sort of stabilize iron into the solution while taking the rest of the impurities out. So when the impurities want to come out, the easy thing is iron actually wants to come out first before the impurity wants to come out, which would defeat the whole purpose of getting it into the solution. So we had to go stabilize iron in a form that it will want to stay in the solution while we can take out other impurities. So we had to sort of solve that problem in a way which is opposite of what the rest of the mineral processing does, because for them, they don't want iron. For them, it's easy. They just allow iron to come out of the solution. So we had to go solve that problem. And the third issue is that unlike other metals, iron has multiple what you call charge states. So think about iron has what is called a 3+ ferric and a 2+ charge state ferrous. So these are different states in which how much deficient the electrons are in the outer shell of an iron compound or a metal. And while most other metals only is in 2+ charge state, or it's a metal. So it's just like that transformation as a result is easy. And what happens in case of iron is that because it has a 3+ and a 2+ charge state, it can easily shuttle between the two, between 3+ and 2+, and not go to the ground state of being a metal. So if you don't do these things in a way, you lose a lot of energy and have very poor efficiency with which you will extract iron. And we had to sort of address that as well. But at the end of the day, economics is very critical. So energy resource is a critical cost factor in the economics. So we had to go solve for that. So there were three unique challenges we had to go address that. Having said that, there's a lot of other know-how that is available from adjacent fields that we brought in. And as a result, once we solve those key technical hurdles, we have been able to scale faster because now we're relying on lots of stuff that's available out there to scale.
And as you scale, I'm picturing, is there like a industrial automation component to this where you're kind of dipping this steel electrode in, collecting all your iron, bringing it out, extracting it somehow from that electrode?
Yeah, there is. It's at the end of it, it's a chemical plant where the front end of the plant is really taking ores into solutions. There's a lot of chemical engineering, chemistry is happening on the front end. But at the back end where iron being extracted, just think about, these are automatic cranes that just go into and extract these electrodes out of tanks where they've been sitting in while extracting iron and getting deposited. And then these cranes just come in automatically and grab the electrodes they need to harvest and then take it to a station where you then detach iron from that electrode, and then they get washed, and then it's like a 20-minute cycle. They're back into the same location, extracting more iron.
Cool.
So like
and this is happening. This is happening today in Boulder.
This is happening today in Boulder. That part of the step of extracting, any metal out of a solution, it's actually done today also for other industries like copper and zinc, actually. So that industrial automation, as I said, it exists. We're just deploying it to iron making and leveraging what's available at scale, already at scale. I mean, industry has taken 20, 30 years to figure that out, for other metals and optimize that.
You mentioned cost. As I understand it, you're selling iron, like 99% pure iron to steel makers, or to Nucor as your example. Why are they choosing to buy your iron over other iron?
Yeah, I mean, look, at the end of the day, we have to supply this iron that is not only have lower emission profile, which is good for the environment, but do it in a way that is cost effective. So it has to be comparable to the way incumbent iron and steel can be made. So what we've shown is that our process has inherent advantages in economics that allow us to get to parity or near parity with how iron is being made today. And big part of those are economics levers that we are turning. What are those? One is about 40% of the cost of iron making today, you are feeding those high grades of ores that I mentioned. Okay. Now we are taking grades of ores that nobody is able to use. So that's 40%, which is an operating cost. We move that as a lever. Okay, great. The second largest operating cost in making iron is your cost of energy. Today we use coal. What comes closest to displacing coal is renewable as a resource. And there we don't seek a base load power. So we can work with utilities that when there is excess power, we can take that in. But if there is high demand for power on the grid, we can, in order of minutes, turn down the consumption of how much power we are consuming. So we become
just using the cheapest energy.
Yeah. So we become, in a way, grid balancing resource. So by providing that value to the system, as a result, we get the cheapest energy resource that then lowers our cost and economics to make essentially iron. Unlike other forms of iron, we make pure metal, whereas other forms of iron still have impurities in it, which need to be processed downstream. So we only feed forward now pure metallic iron. So as a result, the industry and the customer actually gives us a price premium for giving a value to them and hence reducing their cost. So this is commonly done in steel industry. If you have clean, let's say recycled steel, you get paid more. Simple concept. The same thing, if I don't bring impurity to you and you pay me more, is the idea. So we get higher price. So you can start saying that we are controlling our inputs from a cost perspective, and then we are able to get higher premium on the output. And as well as what we're also doing is we are offsetting our cost for making iron by extracting what's in the impurities and feeding that as co-products as well. So we're looking for other value revenue streams as well to offset the cost of making iron, which is really what the world needs today. So that sort of provides a very good economic value proposition and provides a pathway for making the entire value chain way more sustainable. Everybody from, an ore company that is sitting on that asset that is highly underutilized to a steel maker that is looking for something that is green and cost effective. Everybody wins along the way in the value chain. So that's a big aspect of it. The other is that as the world is transitioning from blast furnaces to electric arc furnaces, because that's only two ways to make iron. Either you can go with the blast furnaces or you go with the electric furnace out. As the transition is happening, there is a shortage of iron units effectively that can be put into electric arc furnaces. So this industry is today, and the transition in the next 10 years is highly supply side constraint, where with this transition, there's an opportunity to supply iron. Actually, iron doesn't matter what color it is. It's green, blue, whatever it is. And the industry will take it because just there is shortage of iron units to help with this transition, which is great news for somebody like us. You have the demand. So we are seeing that also on our end, where we have announced MOUs and offtake commercial and pricing structures with many of our partners already. And we're seeing that on the demand side as well.
Talk about that kind of scale. Like, how big is that demand relative to what you're able to do today, or you expect? I mean, I imagine it's it's massive, right? So what do you need to do to scale to get to a place where you can be a significant player in that?
Yeah, I mean, look, first of all, the steel industry is $1 trillion, and the iron making is already $600 to $700 billion a year. I mean, that is the served available market that we are trying to address. The shortage that I was talking about, in North America alone, depending on who you talk to, could be anywhere from 5 million to 7 million tons of this material. Europe itself is like maybe 10 million tons of that material has a shortage of that kind of thing. Coming out of the gate as a technology that we are trying to scale, we are trying to demonstrate a commercial scale project, which will be somewhere around 200,000 ton, probably going to million ton. But I just told you there's a 17 million ton of demand already. So in the grand scheme of things, it's a drop in the ocean, but we have to go through the step to demonstrate the commercial viability of what we are doing at scale, economic viability, qualify more products that can adopt our iron into various applications, then think about the next, which will be the hyperscaling of that solutions by building bigger plants and making regional plants across the globe, because steelmaking is a global industry.
Is that the goal then with the Series B, to get to that million ton production?
The goal with the Series B is we are operating 2 pilots right now. The goal of Series B is to build a demonstration plant right now. And it's not full commercial yet. And the reason we have to take that step is that in order to finance a full commercial plant, let's say 200,000 ton and or above, we need to have guaranteed offtake agreements. Now, in order to have a guaranteed offtake agreement, the steelmaker wants qualification product. Okay. Now, the scale at which the steel is made today, in an electric arc furnace, a typical furnace is a 200-ton furnace, meaning 200 cars have smashed together and melted in 1 hour. Off you go. And that's just one heat, what they call one heat. And they want to put, 40, 50 ton of our material into that heat to qualify into a coil. And then that coil is going to get stamped into part, let's say anywhere from car part to, to a washing machine, that it has green steel on it. So to qualify that thing, we need tonnage here. So the whole demonstration plant purpose is not only demonstrate the technology at bigger than the pilot scale, but largely have enough tonnage to qualify the products and build a commercial pipeline in terms of offtakes, so that then can be used to then finance the commercial plan. So that's, I guess, path we are embarking upon to bring the technology to the market. And obviously you have to do that because as a startup, you're not bankable. What's called, bankable, have the balance sheet that we can just take and deploy $1 billion here and $1 billion there and go, all right, let's just go do it. If you build, they will come.
Right. Yeah, this is that kind of project financing, first of a kind financing that everybody talks about.
Correct. So we are
really
living
tough
that
to get.
We are definitely living that and driving that path forward. So the Series B was done to get that middle step of getting the products qualified, and then the next round, which will be the project financing round to build the commercial plan. So we are rapidly deploying the capital to, as we speak, for building a demonstration plan as well as siting and looking at where are we going to go build the commercial plan, for example, and how quickly we can bring and take this thing through full scale journey.
I'm curious, looking ahead, kind of what time scale is that on to where you have that commercial plant, and then what is your kind of vision for Electra even beyond that? What kind of impact do you want to have on this global market?
Our goal is that, and this is sort of tied with what we're seeing in the market side as well, is that we want to be completely commercially qualified with a commercial plan for the end of the decade and hopefully sooner. And the reason we're trying to do that is we believe the big transition moving away from black furnaces is post 2030. Right now, a lot of things are getting qualified. I think industry is looking at what are different solution sets that are available, developing the beachhead markets and application, but the bigger transition is 2030 and beyond. And we're basically trying to align ourselves to being in the market with a fully commercially viable solution. And from there, the strategy is with partners, regionalize this thing and make regional hubs for iron making, and making iron where electricity is available or can be moved logistically. And it is also close to steel making demand centers, but you don't have to make iron where steel is consumed. Iron moves very nicely to where steel can be consumed. So that's how we see the evolution with the regional hubs. Beyond that, we also see application of iron. As I said, it's not only an essential metal for steel, definitely is needed, but iron is also, pure metallic iron specifically, is also an energy resource, meaning you can store energy in it. So iron is used for, let's say, iron phosphate as an example. So you think about energy transition, and that EVs are moving towards batteries that are lithium iron phosphate, plenty of iron in that battery itself. And ideally, you need pure iron as a feedstock to make that. You can make iron-based batteries like folks like Form Energy are doing, or ESS is doing, that you had in your show very recently. So you think about that application, they are cycling iron back and forth as an energy storage. But at the end of the day, they need iron. Where is that iron coming? They need cost-effective iron to make a cost-effective battery, for example. So you have applications in energy storage for iron. And last but not least, where all of this leads to is that it's my vision that, and it's my belief that since this planet is made out of iron, we forget that actually our planet is actually made of iron, and it does lots of good things for us on this planet. Every time we take a shovel into the ground and bring dirt out, we actually are extracting iron along with lots of other things. So if you look at every other mineral processing that we do today, if you look at what's in its tailing, actually is lots of iron as a waste. So my point being is that the world can learn how to extract iron from every mineral we dig out of the ground. My point is that you will find lots of other things with it, or the planet is made of iron. So example being is that, the biggest critical earth mineral mine in the world is in Mongolia, Inner Mongolia. Well, it is first an iron ore mine because you don't find that mineral along with it. It's sort of buried in the matrix of iron. So my point is that if we can start making economically iron, instead of thinking of being a waste with every other mineral processing, we can also help a lot of other material that are needed for energy transition. So it is as big as it can get, Dylan. It's just that I have limited time right now. Only can focus on one thing, one step at a time right now.
Okay. So I have 3 questions I ask everybody at the end of each episode, and these can be quick answers. The first is, how optimistic or pessimistic are you about the future of the planet, and why?
I think for me, that answer is, the question of climate transition for me is not, can we do it, or is it possible to do it, but rather than when can we do it? And that's the optimistic part of it, that I'm very optimistic that we have the tools, we have the solution, we have the ingenuity to help with this transition. But if I flip that coin, that's where the pessimism also comes in, is that I think we have limited time. And with everything that's going out there, I think we're losing momentum and the focus that we need to make this transition happen as quickly as possible. So we're up against time. And my concern and the pessimism is really around that we're likely not going to hit the 1.5 degree target that were originally set, not for the lack of technology or the solution sets or the lack of policy, just having a call to action, almost like what we had for pandemic. And when we put that, our minds together, we were able to solve the problem. The whole world,
that level of urgency.
right? Yeah. There's urgency. The whole world came together and we did it. And so it's the same thing for me, both sides of the coin. I'm optimistic, but my concern is around the timelines.
Who's another company or individual doing something to address climate change that's inspiring you?
For me, it's a whole class of companies, if I can broaden that answer to. I kind of alluded to this point, and as I've sort of gone through this journey with Electra, it is becoming more and more apparent to me is that in order for this energy transition to happen, what it is constrained is by resources, and resources that are actually on our planet. And these are resources that are available, but they are locked in the ground. Okay. An example for that is what we are trying to do. And, trying to sort of make this in a sustainable way, in a more way that doesn't create more harm or negative. There are more positives than negatives to the planet. But take that as another example. There is heat buried underneath our ground. So a good example is Fervo Energy that has been in the limelight recently, and they're trying to extract the heat from the ground. So that's a resource that is available. We know how we can do it, but we just need to tap into it and start using it. And in that class, there are a lot of sister companies and portfolio companies around, the investors I know of, that have a very similar, I would say, vision to it, where they're applying, in a way, similar ideas, okay, and trying to sort of work through that problem as well. So that's why we say that, we're trying to reinvent iron making from the ground up, but ground is where you got to go look for the answers. We actually don't realize that they're right beneath the ground we are walking on. And planet Earth, as a result, has been very kind to humanity. We have the resources. We just have to do it smartly.
I love that. Planet Earth has been kind. What advice do you have for someone not working in climate today who wants to do something to help?
I believe that it is our collective action, first of all, that helps with this transition. So if you have the skill sets, there's a lot of opportunity to make an impact, first of all, in the climate space. You look at us, we are about 150 people, and we're looking for people, not only just scientists, but everything from HR to projects to be able to do marketing, sales, and operators. So there's a lot of opportunity for growth and deploying the skills we have learned, or like what we are trying to do, bring in knowledge from other industries. And the same thing, I think the talent can be brought in from other industries and make an impact. That's one aspect of it. Other aspect of it is we should not underestimate what each one of us can do. So with that is to take a bike to a grocery store and save that one trip of a car. It's good for the environment. If you have a pen, you can write to your congressman or to a senator to help push for what is important. All of that counts, in my opinion. And we should not underestimate the power of that change. But the big change always happens is when we can bring that together and make a collective change, kind of a thing. And then it becomes even more impactful in a way. So as much as I can, ride my bike back and forth to work, which is one way to do it. But by starting the company, I put 150 people together in a way. And the next 100 people you bring in, that can make a massive impact. And that's the lever that is what I'm talking about, is, the collective change. All I will say is that my advice to those or sitting on the sidelines. One is call of action. There's a lot to do, and don't underestimate your transferable skills that can be applied to this industry, but also don't underestimate what you can do as an individual too. Both of them count.
Love it. Sandeep, thank you very much. I appreciate your time. I love what you're doing.
Well, thank you. It was a pleasure to be here and I really enjoyed our conversation, Dylan.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.